So here I would like to correlate dislocation with materials which we see around us. So here I have shown a picture of a coffee and coffee in it, and you can see air bubbles which are formed on the froth of this coffee. I had mentioned you about a bubble raft. I think you would have seen about bubble raft models on the internet, and you can see that these air bubbles on coffee or on this froth closely resembles to this bubble raft. You can see there are bigger air bubbles, smaller air bubbles, or there are no air bubbles which can correlate to substitutional or intentional uh, or interstitial atoms or vacancies in it or some defects in it, grain boundaries. So I leave it to you to observe this picture very closely. And if you have some pictures like this, you can share with me. This is a picture shared with me by Sarvesha, who is our PhD scholar. And you can see here that you can relate it to a formation of an edge dislocation. Let's say this is an half plane and I consider this is other planes. So I can see that there is a formation of an edge dislocation. Now when I talk about edge dislocations, the moment of edge dislocation is considered to be equivalent or analogous to moment of a caterpillar. Let's look at how caterpillar moves. So we have seen how caterpillar moves, and it is analogous to the moment of an edge dislocation. How is it analogous to moment of an edge dislocation? You can see that when edge dislocation is here, there is breaking of bonds locally, and you can see that caterpillar has moved its legs up at this location, which can be considered as analogous to breaking of bonds here. And when dislocation moves further, there is a breaking of bonds at this position, and you can see the caterpillar has moved its legs up at this location. And as this motion continues, you can see there is a formation of a step which is called as a displacement vector and is quantified using a Burgess vector. And thus the caterpillar moves in this way. So you have locally breaking and making of bonds which can be related to the motion of caterpillar. So you can say that all bonds are not broken at the same time, but rather there is a breaking of bonds locally. And we would have seen this when there are dislocations in the crystal, the theoretical yield strength is much higher as compared to experimentally observed yield strength, and that we have related to this local breaking of bonds, which reduce down the energy to move the dislocation. Now coming to a motion of dislocations, let us consider a glide of dislocations. So here I have shown a pure edge dislocation and pure screw dislocation, and when they move, there is a creation of step by Burgess vector B. So let's consider this edge dislocation. So this is a dislocation line marked by a red line, and this is a Burgess vector B which is perpendicular to the dislocation line. Let me write it down. So you have this is as a T vector. Have this is T vector and Burgess vector is perpendicular to the dislocation line. And I apply a shear stress, and this dislocation line moves. It moves in this direction. I have marked this direction also. The direction of motion of this dislocation line is along this way, and it creates a step. In case of a screw dislocation, you can see the Burgess vector is parallel to the dislocation line. Let me write it down here also. So this is our T vector. This is T vector, and Burgess vector is parallel to the dislocation line, and we apply a shear stress, and the direction of motion of this dislocation line is along this way, and when this dislocation moves completely, it creates a step. So you can see that dislocation is moving here in this direction and it is creating a step in this fashion here. So there are certain critical observations from this. Let us write it down. For pure edge dislocation, the dislocation line is perpendicular to the Burgess vector. The dislocation line vector is perpendicular to the tau, that is shear stress applied. The tau shear stress is parallel to the Burgess vector, and the direction of motion of dislocation line is perpendicular to t vector. We know that the dislocation line is perpendicular to the Burgess vector. We have seen this. Dislocation line is perpendicular to the tau, that is this tau which is applied. The dislocation line is perpendicular to the tau. Tau is parallel to Burgess vector. This tau is parallel to the Burgess vector, and the direction of motion of dislocation line is perpendicular to the t vector, tangent vector. So you can see that this is our tangent vector, a dislocation line vector, and the motion of it is perpendicular to it. Now let's consider for a screw dislocation. The screw dislocation is defined as a t vector is parallel to Burgess vector. Here in this case the t vector is parallel to tau, and tau is parallel to Burgess vector, and the direction of motion of dislocation line is perpendicular to tangent vector. So here in this case, let's look at t vector is parallel to tau, the t vector is parallel to tau, tau is parallel to b, tau is parallel to b, the direction of motion of dislocation line is perpendicular to t. So let me write it down. So here we are having this t vector and its motion is perpendicular to t vector. So this is our t vector and its motion is perpendicular to t vector. So there are two important observations from pure edge and pure screw dislocation moments. Is like tau is parallel to Burgess vector, or some component of shear stress must be parallel to Burgess vector to move the dislocation on the slip plane. And the second important point is the direction of motion of dislocation line is perpendicular to tangent vector. So you can see that from both the cases, in both screw and edge dislocation, the t vector or the direction of motion of dislocation line is perpendicular to the t vector. Here in this case also the direction of motion of dislocation line is perpendicular to the t vector. So these are the two important observations, and this is not just valid for pure edge or pure screw, it is valid for mixed or other type of dislocations too. So let's consider this slip plane and let's consider this dislocation line. Let's mark the Burgess vector. Let's mark this Burgess vector and let's apply a shear stress. And this dislocation line will demarcate between slipped and unslipped region. So when I say a direction of motion of dislocation line is perpendicular to tangent vector, so you have tangent vector varying at every point that we have seen for this dislocation line. So the motion of this dislocation line will be perpendicular to the t vector at every point, and you can see that when this dislocation moves, it will move in this fashion, which is marked by these arrows, and the dislocation will move in this fashion and it will reach at this position. Similarly, if I consider a loop also, which gives me slipped and unslipped region, and the t vector will be moving or will be changing at every position, and the motion of this direction of motion of this dislocation line will be perpendicular to t vector, and thus it will move in this fashion, which is marked by these arrows, and when it moves, it will move in this fashion, which is perpendicular to its t vector. So this is an important point. The direction of motion of dislocation line is perpendicular to its tangent vector. So there are two important points to be noted from this slide is like the shear stress. Now the component of shear stress must be parallel to Burgess vector to cause a glide of dislocations on the slip plane. And the second important point is the direction of motion of this dislocation line is always perpendicular to its tangent vector. Now when I talk about glide, let us consider crystal structure and some important terminologies here. In case of FCC, we have seen the slip direction is 110 and slip plane is 111. In case of BCC, we know that the slip direction is 111, but there are different slip planes like 110, 112 and 123. In case of HCP, you have 11 bar to 0, that is a slip direction, and you have slip planes which are 0001, 1 bar 100, 1 bar 101. Now in case of BCC, the slip or the glide in BCC can be understood using this simple model of pencils. So this is a stack of pencil and it is being sheared along a direction which is along the pencil direction, which is nothing but the perpendicular direction to this screen. And you can see that the slip direction remains the same, but the slip can occur on any planes. And that is why you can see there is a zigzag motion or zigzag features on this slipping of pencils, and this is called as a pencil glide. In case of BCC metals, you can see this pencil glide which is occurring and which resembles to the glide of these pencils. That is why most of the papers or most of the articles or books refer the glide in BCC as pencil glide. Now when we talk about dislocation moment, here comes a very important terminology, that is a cross slip. Now let's understand what is cross slip. So we know that pure edge dislocation and we know a pure screw dislocation. So pure edge dislocation is defined on the slip plane as a tangent vector perpendicular to the Burgess vector. And this dislocation line demarcates the slip region and unslip region. Similarly, for a screw dislocation, the tangent vector is parallel to the Burgess vector, where this dislocation line demarcates between slip and unslip region. Now, if you look at this edge dislocation carefully, you can say that, let me write it down, this B vector is perpendicular to tangent vector, and thus if they should be on same slip plane, and thus they need a specific plane also. If you consider, they have to glide on a specific plane, because if two vectors are perpendicular to each other, they must lie on a specific plane. And thus, if this dislocation has to move, it cannot move on any plane. It has to move on a specific plane. Thus, it has a unique slip plane for gliding in case of a pure edge dislocation. Now, in case of a pure screw dislocation, it can glide on another plane. Why? Because the Burgess vector is parallel to tangent vector, and thus there can be other slip planes which can be available, and this screw dislocation can glide on that slip planes. Now the question is, how does this glide happen on another slip plane? Now let's look at cross slip of a screw dislocation. So let's consider this is a slip plane, and let us mark our screw dislocation, Burgess vector parallel to dislocation line or a tangent vector, and let's apply some shear stress, and with the influence of the shear stress, this screw dislocation will move on this slip plane. and this is called as a glide of dislocation. However, now this t vector is parallel to Burgess vector, and this is another slip plane which is marked as slip plane 2. This dislocation can glide on this slip plane based on the situation of shear stress or obstacles on this slip plane. This dislocation, this screw dislocation can glide on this slip plane, and this can glide in this fashion. So this is called cross slip of a screw dislocation. This is slipping on one plane and then it cross slips on another plane. That's why it is called as a cross slip of a screw dislocation. As I mentioned you, let me write it down. Edge dislocation cannot cross slip. Why? Because it needs a specific plane. It cannot glide on any plane. Why it needs specific plane? Because Burgess vector is perpendicular to tangent vector. So edge dislocation will never cross slip, while screw dislocation cross slips. Now let's look at cross slip in more detail. So let's consider this abscissa structure, and I have marked 111 plane over here, and let us consider this dislocation a by 2 110 type, and let's consider the dislocation line is parallel to this Burgess vector, so that is, it is a screw dislocation. And let's consider this another plane which is nothing but bar 1 plane. Now when I see this situation, I can draw a schematic over here. So this is our 00 bar 1 plane, and this is 111 plane which is marked over here, and this is a dislocation which I have mentioned, and this is this plane, that is bar 1 plane. And when I apply some shear stress along the Burgess vector and this dislocation moves, so it will move and it may cross slip on this plane now. So it cross slips on this plane because this is also a slip plane, and this is a Burgess vector, and this is the Burgess vector is parallel to the dislocation line. So this is a screw dislocation, and thus it can cross slip from this plane 111 plane to bar 1 plane. So it cross slips, like it moves on this plane, slips on this plane, and then it cross slips on this plane. So this is how a screw dislocation can cross slip. Now let's consider another scenarios here. So let's consider this 111 plane, and let's consider this dislocation loop, and let's consider the Burgess vector to be along in this direction. And when we apply a shear stress, this dislocation loop expands. How it expands? The motion of this dislocation loop will be perpendicular to the tangent vector. So it expands in this fashion, and you can see that there is another plane, that is 1 bar 1 plane, and this Burgess vector is parallel to the dislocation line here. So it becomes a screw type here. So let me draw here. So when I consider at this location, the Burgess vector becomes parallel, and thus here it has a screw nature or screw character, and thus this region here or this part of this dislocation loop can cross slip or can move on this plane which is 1 bar 1 plane. And let's say this Burgess vector is along bar 101 direction. So when I have this screw nature or screw character here, this loop or this dislocation can cross slip over here in this fashion, and it can expand on this 1 bar 1 plane. So this procedure is called as a cross slip. Now when I still keep applying shear stress, what happens is that this loop can cross slip and can again come back to a original slip plane or another 111 plane in this fashion, and then it can expand on this 111 plane too. This phenomena is called as where the loop is being expanded, it is called as slip here, which is happening. This is where the screw dislocation or the screw character cross slips on another 111 plane. It is called as cross slip, and here when it glides on again back to the original 111 plane, this is called as a double cross slip. So you have a slip, cross slip and double cross slip of a screw dislocation. Why this happens? As I mentioned to you, let me write it down again. Why this happens? Because Burgess vector is parallel to tangent vector and they don't have specific planes, so they can glide on another planes. Another planes means another slip planes. It may be specific. Another slip planes. So you have slip, cross slip and double cross slip phenomena for screw dislocation. With this, I will stop here.